You know, hydrogen gets talked about all the time as the ultimate clean fuel, but it's got this one huge problem. It's the lightest gas in the universe, which makes it an absolute nightmare to transport. Today, we're going to dive into the incredible chemical journey to solve that exact problem by essentially bottling hydrogen into a safe, easy-to-handle liquid. Okay, so let's start with the big picture, the dream. We're talking about a world where clean hydrogen made from renewable energy can be pumped into ships, trucks, and yeah, even your car, just as easily as gasoline is today. It's a fantastic vision, right? But it all hinges on solving one massive critical question. How in the world do you bottle up the lightest element in the universe and ship it across an ocean? I mean, compressing it or chilling it down to a super cold liquid is not only expensive, it can be pretty dangerous. The real bottleneck here isn't making the hydrogen, it's moving it. And this brings us to a really ingenious solution, liquid organic hydrogen carriers, or LOHCs for short. The whole concept is so powerful because it's so simple. You take this special organic molecule, that's your carrier, and you chemically charge it up with hydrogen atoms. Suddenly, you have a stable, safe liquid. Then, whenever you need the energy, you just use a catalyst to discharge the hydrogen gas. And guess what? The carrier molecule is empty and ready to be recharged all over again. So let's really get into the story of discovery, which for us starts back in 2021. This is when researchers really started digging in with a promising LOHC molecule to see if they could actually get the hydrogen back out efficiently. The molecule they were working with was called H12MVP, basically a liquid that's just packed with hydrogen. But here's the thing, just heating it up doesn't really do the trick. To coax that hydrogen out effectively, they needed a kind of chemical matchmaker, a catalyst. The whole game was to find the absolute perfect one. And this is a perfect snapshot of their core experiment. What they did was they took these tiny particles of palladium, a precious metal that's fantastic at this sort of thing, and they placed them on different metal oxide supports. You can think of it like testing different types of soil to see which one helps a plant grow the best. They measured everything, how much hydrogen came out, how fast it happened, and maybe most importantly, could they use the catalyst more than once? Now, this is where it gets really interesting, because they found a classic trade-off. The catalyst on the alumina support, it was a speed demon, the fastest by far, getting a 75.8% hydrogen yield. But the problem was, after just one use, its performance just cratered by 33%. On the other hand, the catalyst on the Sirius support was a little bit slower, getting about 67.1%, but it was an absolute rock star when it came to stability. You could use it over and over and over with zero loss. So that was the big question. Do you go for speed or you go for stability? Well, you know scientists, they don't like to choose. They want it all. So the very next year, the research zeroed in on how to overcome this trade-off. They wanted the speed, they wanted the high yield, and they wanted the stability. So their new strategy was to try a totally different kind of support for the catalyst, zeolites. Now, these things are amazing. They have this microscopic honeycomb structure, which gives them a massive surface area, and crucially, a really acidic surface. The thinking was that this acidity would help nudge the reaction along, hopefully boosting both speed and efficiency. And yep, here are the results. This graph shows you exactly what happened when they played around with zeolites that had different levels of acidity. The outcome was crystal clear. The more acidic the zeolite support, the more hydrogen they managed to pull out. And the best they hit was a 64.7% hydrogen yield, and that was with their most acidic zeolite catalyst. Now, this was a fantastic step forward. It proved that you could really improve performance by fine-tuning the catalyst's environment. But you know how science works. The community was already asking the next question. Can we do even better? What if we change the LOHC molecule itself? And you know what? That question led to a massive breakthrough in 2023. Instead of just tweaking the catalyst, a team of researchers developed a brand new LOHC molecule, one that was designed from the ground up to be super efficient. Say hello to MBN, or methylbenzyl naphthalene. On the left, you can see its simple, elegant cycle. But on the right, well, the proof is right there in the data. Just look at that blue line. That's MBN. It releases its hydrogen way faster and much more completely than the older LOHC types, like that one in red. This wasn't just an improvement, this was a total game changer. So what made MBN so much better? Well, the secret sauce is something called dehydrogenation enthalpy.
It's a fancy term, but it basically just means the amount of energy you have to pump in to get the hydrogen out. MBN was specifically designed to have a really low enthalpy, meaning it gives up its hydrogen much more easily. That makes the whole process way more energy efficient.
And how efficient are we talking? Well, when they paired it with a platinum ceria catalyst, the system achieved an incredible hydrogen yield of over 99%. I mean, wow. It really seemed like the perfect solution had finally been found. But as you know, science is never quite that simple, is it? So with this near-perfect efficiency, a new, unexpected challenge popped up. The very same reaction that made the MBN system so powerful was also creating a tiny but very problematic side effect. Basically, the high temperatures they needed for the reaction were causing a few of the MBN molecules to react in ways they weren't supposed to, creating these unwanted byproducts. Now, they weren't dangerous or anything, but they basically gummed up the works, which reduced the purity of the hydrogen and prevented the LOHC liquid from being reused perfectly. So, the final piece of this puzzle was figuring out how to tame the catalyst just a little bit. And the solution, which came out in a 2025 paper, was just brilliantly simple: catalyst doping. By adding a tiny, precisely controlled amount of sulfur to the platinum catalyst, they could dial back its activity, just enough to keep it powerful for releasing hydrogen, but not so aggressive that it started creating those pesky byproducts. And the results were just stunning. I mean, this bar chart says it all. The standard catalyst on the left created a pretty significant amount of byproducts, but the sulfur-doped catalyst, that formation was practically eliminated. They had found the final tweak to perfect the system. Okay, so let's just step back for a second and look at the absolutely incredible progress that was made in just a few short years, all happening at the molecular level. This timeline really just tells the whole story, doesn't it? From figuring out that fundamental trade-off in 2021, to improving the catalyst in 22, then completely redesigning the carrier molecule itself in 23, and finally, perfecting the reaction in 25. Each discovery was a crucial building block on top of the last one, leading to this highly refined and super efficient system. And it all brings us right back here to this initial vision of a clean hydrogen economy. This isn't just some far-off dream anymore. The research we've just walked through, these are the tangible chemical engineering breakthroughs that are actually making this picture possible. It's just a powerful reminder that sometimes the biggest changes in the world start at the absolute smallest scale. These tiny molecular innovations are literally filling up the tank in your car.